Hello, and this week's video is going to be about logarithms. So this is just going to be really the basics of logarithms and how we use them and why we use them. So how about let's start by looking at a scenario in which you might want to apply a logarithm. So this might show you like why the logarithm was actually developed. So say you had a certain rate. For example, say you have a population, right? So say you have a population that triples every year, and it starts with one person, which I know isn't realistic, but for the case of this problem. And then you want to find in how many years will there be 100,500 people. So how might you start and go about this? Well, you would probably say that, each year, let's define a year by the number of x, right? Or the variable x. And we know that it triples every year, so we know that 3 to the power of x is going to be equal to the population. And in this case, we want the population to be 100,500. So 3 to the power of x is going to have to equal to 1,500. And do you see where you run into problems? Is that maybe with the skills that you have right now, or the more like the knowledge that you have right now, you can't really solve this. You can go ahead and try to guess x. You can say, well, 3 to the power of 2 is 9, so that's probably not enough. What about 3 to the power of 20, 3 to the power of 5, 3 to the power of 6? And you can go and round, but that really does not get you an accurate answer. And where logarithms come into play is to actually help us derive what x is. So, and this is set up like a function, for example, like sine of x. It's quite different, but you can view it in a similar way, that it's a mathematical tool that you use to find a value that you might need. So what I'm getting at is that the logarithm with a base of 3 of 100,500 is going to equal to x. And if we actually go and evaluate this, x will equal around 10.4, let's say 484. And if you want to check this, you can say, or you can type into your calculator, 3 to the power of 10.484. And what will you get? Well, because we rounded to 3 decimal places, you'll get 100,493.79, which is quite close, but not quite there yet, and that is because we rounded. And in cases of exponential models, rounding really does. A little change makes a big difference in your answer. But you can see how we use logarithms to solve this. So basically from this, we can see that we use logarithms to find a missing exponent. If your exponent is the variable that you're trying to look for, use the logarithm. And so maybe you have realized yourself over here how this works, but let's try to generalize this a bit. If you have, let's say you have b to the power of x is equal to a, and you know b and a, right? Then x will equal to the logarithm base b of a. So in a logarithm, this is the base, and this is of. This a is the logarithm base something of a. So I hope that makes sense. And basically, what you are doing when you look at this is that you're asking yourself a question. If I raise b to the power of x and get a, you don't know the x. So you're asking yourself the question, what power do I have to raise b by to get a? So this right here is your key question, and it's crucial you understand it, because it's not just an equation. You must understand what you're actually doing in order to be able to use it correctly when it might not be just as simple as this. So let's look at a more basic example in which we just simply look at the mathematical aspect of it. So let's say we have 5 to the power of x is equal to 26. And we want to find what x is. So have a go at yourself, try to set the logarithm up. we would know that x is equal to logarithm base 5, because what are we raising to the power of x? 5, of 26, because that's what we want to get. So if you actually go and calculate this, your x is approximately 2.02436919, etc., etc. So these are obviously some irrational numbers. We can just round this to 2.024, let's say. And this totally makes sense. 5 to the power of 2 is 25. 26 is just one more. So this answer for x is pretty reasonable, isn't it? Okay, let's do one last example. So let's say you have radioactive decay that doubles every minute. So the amount of particles doubles every minute. And you want to find in how many minutes will there be 27 atoms. So let's take a look at this. So we know that it doubles every minute. So if we have x is equal to the number of minutes, then we know that 2 to the power of x is going to equal to the particle number. And we know that in our case, we want to find when the particle or atom number is 27. So we say that 2 to the power of x is 27. So how do we set this up? Well, we know that x is going to equal to the logarithm base 2 of 27. And if we actually calculate and round it, that's going to be around 4.7549, let's say that. And another way that we can approximate this is simply by looking at the graph. So if your graph is y equals 2 to the power of x, which is what we were looking at over here, so in this case, y would be the number of particles. And let's find 27. So this is our 27 right here. If we take a close look, this is very, very, very close to what we got over here. 4.75. That right here, it's right around there, right? This would be your 4, and this would be right around what we got, right around 4.75. All right, so I hope you have learned more about logarithms, and I hope you have actually understood why we need them and also how they work. I hope you don't just look at this and see an equation, but more of a procedure that you can use to answer the question of what power do I have to raise b by to get a. The main idea is finding the power to which you're raising something. All right, so I hope you enjoyed, and see you next week.